Hi. In previous tutorials, I talked about simple Navier-Stokes solvers in FEniCS. In this tutorial, I will discuss Oasis, which is a very robust CFD package developed in FEniCS, originally by Michael Mortensen and Christian Wallensenstadt. So this paper discusses the software and also the CFD solvers that it has, the different finite element solvers that is implemented. Later, I will provide detailed tutorials on these different approaches to do CFD with finite element. But for now, we're just going to talk about how to use Oasis. So this is a GitHub directory for the original Oasis solver. I'll provide the link in the description box. And this original version is compatible with FEniCS 2018, which is the version of FEniCS that I've used in most of the other tutorials that in this series. But the version of Oasis that I've used and I've modified, I'm going to talk about today, is compatible with FEniCS 2017.2. However, if you prefer to use this latest version, you can and use the features that I've implemented, you're welcome to copy them into the latest version and use them. So I'll talk about that today. Okay, so so here is my version of Oasis that I've shared in the GitHub directory. So there's a job file that you can see here. So this is essentially how you would run this run Oasis. You will call the ns-fracstep.py file. So this is kind of like a main file. That's the fractional steps method for solving Navier-Stokes. And then you define your problem, which is a problem under the problems folder, which I'll talk about in a moment. And then you can save your output to a log file, to the log to a log file. So here you have two main codes. You have the ns-fracstep.py and ns-coupled.py. So these are two broad finite element approaches that you can do CFD, the fractional steps method and the coupled method. Most of the papers, most of the work that I believe that Christian, one of the main developers of Oasis, has done is with the fractional step solver, and that's also what we've used, which is nice because it's pretty good for unsteady problems. And also the other nice thing about this fractional steps method compared to the coupled method is that it doesn't require necessarily stabilization. So that gives you really accurate, minimally dissipative finite element solver. So I'll talk about this today. So this is the but before I do, let me also briefly talk about the papers related to Oasis. So one of my favorite papers that comes from David Simon and Christian, and also Oasis Khan, is this paper, which is a very inspirational paper that talks about high-resolution CFD strategy, which is what they do with Oasis, with super high-resolution quadratic elements, so P2P1 elements, very, very small time steps, and they get results that are different from the normal resolution strategy, which is what most groups in the field of cardiovascular flow modeling use. So very, very nice inspirational paper that inspired a lot of work that my group did. So also, this group has several other papers that uses Oasis for high resolution CFD modeling, and we talk about advantages and studying things like flow instability. So I've also used Oasis in several publications. I'm just going to point out to 3 of these papers. So in this paper, we use Oasis to develop a new residence time-based blood rheology model. So in this case, we coupled a standard non-Newtonian model to residence time, because we know that blood, the non-Newtonian effects really become activated when red blood cells are exposed to high stagnation. And this is something that all current non-Newtonian models ignore. So we were able to use Oasis to couple particle residence time calculations with a non-Newtonian model. Another example of that is this paper, where we coupled Oasis to an ALE type growth model. So this was a two-way coupled shear stress driven growth model, where you do your CFD simulation in Oasis, get wall shear stress, you grow the stenosis by moving the mesh and doing mesh smoothing, and then you smooth the mesh, you update the mesh, and you rerun the CFD simulation. So you can do this entire pipeline fully automated using Oasis, and get some nice results like this, where you have the plaque growing. So you're wrapping around your Navier-Stokes solver with different growth stages, and also that are driven by wall shear stress. And finally, as the last example, we have also used this Oasis for doing airflow modeling in lung airways. And in this paper, what we did was that we used the large eddy simulation tool provided in Oasis to do turbulence modeling with LES, and we also validated our results with magnetic resonance velocimetry measurements. So I also encourage you to look into this work. Okay, great. So now let's get into the details of Oasis. So this is the main folder that I have. I'm going to start by looking at the nsfracstep.py method, which is the main code that we'll be running, and that will call different functions. So there's not much here. So this is just setting up the solvers, and this is the main loop here. So this while loop that you see here is the main loop that you march forward in time, and you save your files, you call your solver, and different things. So now I also have included this one example here in this folder. That's an example where I show you how you can essentially couple, modify this to couple your CFD solver with other things you can do in Python and VTK. So in this case, if I go to the while loop here, you can see that it's much more involved. So this code corresponds to this paper here, this growth paper that I do. So basically, I do a CFD simulation, I update wall shear stress, I grow the mesh, update the mesh, smooth the mesh, and rerun the CFD solver. So I can do all of these things. So you can see I have smoothing filters, I have ALE growth, and all of these are provided by VTK, which I can import here. And I won't talk about the details of this, but this is just one example for you to look at to see how you can, be creative and couple your solver all in Python with other models or other things you like to do. Okay, but for the most part, this is if you just want to do regular CFD simulation, you'll just be using nsfracstep.py. So here's where you call it in your job file. So if you're using another version that you've developed, you would change nsfracstep.py to whatever more involved solver that you have. Okay, now what I'm going to talk about next is the details of this. So this is the nsfracstep.py that I talked about, and then we also have some inputs and outputs. So under common, there is an input-output io.py file. So here you can define how you want to save files, what you want to save, what format you want to save. So specifically here, I provide functionality for saving either as VTK or H5 files. And also I have added wall shear stress calculations here. So here I'm also saving wall shear stress. And so just note that the density here is hard-coded in a CGS unit. So if you're using another unit system, you should either change this or scale your wall shear stress results. But essentially, you could do any kind of post-processing you like here and save those as you're running your CFD simulation. So this is where you could do that. Now let's take a look at solvers. So under solvers folder, we have our solvers. And specifically, so we mainly use the nsfracstep one. So this is what we're interested. And for those of you who are familiar with CMascular, which I talked about in my earlier tutorials, CMascular uses the coupled method versus the fractional step method. So it needs a stabilization because it uses P1 elements. But here we use the nsfracstep method, and we can either use P1 or P2 elements for ultra high resolution CFD simulation. Okay, great. So here you have different versions of the solver. So the Turing method is what I talked about in the simpler tutorials. And but the one that we will be using is the IPCS ABCN. So I think it stands for Adams Bashforth Crank Nicholson. So this is the solver that we will be using, and you can call these in the problem file, which I'll talk about in a moment. So you can specify which solver you want to use within the different solvers in nsfracstep or nscoupled too, but we have never used the coupled method. So everything we've done with Oasis was with the fractional steps method. Okay, so this is the solver. Now, so there are different functions here. So the setup function has some things. So here I've added some functionalities. I've added non-Newtonian modeling, and with certain flags you can specify if you want to do non-Newtonian modeling or not. And also I have added backflow stabilization. So it turns out that in a lot of cardiovascular simulations, we get backflow at the outlet. So there's this very nice paper by my friend and colleague Mahdi Ismaili and Alison Marsden that they talk about this backflow stabilization technique that can overcome the issue of having backflow at the outlets. I'll provide a link to that paper in the description, but here I implemented that, so you can specify with a flag if you want to use that or not. But essentially, this term is what's added to the weak form, is the one that that models the backflow stabilization. And there's a beta backflow parameter that you can specify in the input, which I'll talk about in a moment, which specifies the strength of how much you want to stabilize for backflow. And in this case, I'm assuming that I have two outlets tagged on phase 3 and 4. So if your case, the tags are either different, or you have more than two outlets, or you have one outlet, you need to modify this. Either add more outlets, simply adding or removing the surface integral terms in the weak form here. Okay. So then another thing to note here, there's a bunch of functions here as part of the solver, but another thing that's noteworthy is the pressure solve, where you can implement resistances. So you can calculate the flow, multiply by resistance. So in this case, I'm doing it assuming my two outlets are tagged as 3 and 4, and I'm reading the resistances at the two outlets, and I'm calculating pressure based on the resistance and specifying that as a Dirichlet boundary condition for pressure during the pressure solve. So this is how that's done. So so you see here, I'm assuming the tag 3 and 4 are my two outlets. So if in your case that's different, you need to modify this. And then you have other parts, velocity update and other assembly parts. Okay, so that's the solver. Now, the thing that you'll mostly need to use is the problems folder. So under the problems folder, we go to NSFrag step. First, there's an initialization file, which I'll take a look here. And this has all the parameters we have. So any parameter we have here gets initialized. So, and you can read the description what these parameters are. These are different parameters for your CFD model, and also different solvers for the different steps of the fractional steps method. And you can change all the solvers, preconditioners here based on what's available in FEniCS, and also tolerances and everything. So you could either change things in the initialization file, and that you would do that if you want to change something that's essentially you want to change your default. That's what you're using for all of your cases. You want to change it here. But if there's something you want to change that's specific to a problem, you could define a problem here. So here you can see I have defined a bunch of problems, and you can define your own. So for example, there's some tutorials in Oasis, like for channel flow, cylinder, some simple tutorials that they have here that's also still included here. And I'm going to go over one of the input problem files that I've defined. And this is this AAA problem. So here I am, essentially defining my parameters. So these parameters will override whatever is in the initialization. So if you want to override anything, you would define it here. If you don't want to override, you'll just rely on the initial default parameters. So in this case, you can see I'm defining the kinematic viscosity, the total integration time, 3 cardiac cycles in this case, my time step, my velocity degree. So if you set it to 1, this will be P1 element, first order velocity. If you set it to 2, which is what we do in most of our papers, you'll do P2, P1 element. So that gives you super high resolution mesh. So essentially, if you do P2, P1, you can think about in 3D, your mesh is essentially roughly 8 times what you would get with the first order element. So if you have a mesh that's 8 million elements and you do P2, P1, you can roughly think about it around 60 million equivalent mesh. So really, really high resolution. So here you specify how often you want to save. This checkpoint is something I don't really use, so I've set it to a very high number. You can define if you want to use a non-Newtonian flag, the backflow stabilization, what's the beta parameter, if you want to do resistances, if you want to use H5, or you don't want to use H5, you just want to save VTK, or if you want to, the resistance values, you can set them here, and if you want to save wall shear stress. And then another important function here is the create BCs. So here you define your BC, specifically the inlet boundary conditions. So you can look over this in detail, but essentially you definitely need to update this part. You need to tell it the tag for your inlet ID, which I think in my case is probably 1. And also you need to define this specific to your problem. So in this case, I have provided some codes if you want to do parabolic elastic profiles, but if you want to do uniform, you can modify, you can also do uniform here too. So you have to read through this to, set your inlet boundary condition and the way you want to set it here. Okay, and then here you read the BC node facets XML file. So this is the boundary condition tag file, and also the mesh is also read here. So this is the 3D mesh in the XML format. So it's reading the meshes in XML format, which I talked about how you can create in earlier tutorials. Okay, so that's all I wanted to go over here. But I really like Oasis. It gives you flexibility to change your solver, to use high resolution numerical methods, P2P1 elements, no stabilization, and has great features. And I will be providing tutorials later that will talk in detail about the theory behind this solver, the fractional step solver versus the coupled solver, the advantages, disadvantages, and all of those things. Okay, thank you.